please. So you please mute your mic, and if you want to speak to me, you just unmute your mic and speak. Okay, let us start with the topics of today. Actually, usually it is a doubt clearing session, but I could post the video only on Tuesday night. That's why there was not enough time for the doubts. So time to time, I will take up questions from you if you have specific questions regarding this presentation. But I think many of the doubts will be cleared when this live class is conducted. So our topic is internal forces, axial force, shear force, bending moment, and twisting moment diagrams. These are the basic concepts. Let me first explain what we are after, what we are trying to say. Let us explain what we mean by internal forces. Does that mean that so far we were with only external forces? Now, how could internal forces come into picture? Why we are suddenly interested about axial force, shear force, bending moment, and twisting moment? What are these quantities for engineering sense? So with that, I will say first, let us discuss what is a slender member. So slender member, usually you can say is there are plenty of examples in practice. Actually, the slender members are more efficient in working. Suppose our hands and legs are slender members. That's how we are able to walk so efficiently, and also with hands we can do so many works efficiently, because the technically speaking, a slender member has one of its dimension much larger than the other two in the cross sections, and that's how it can span very large distance with minimum usage of material. But the penalty is that you have to take care of the stresses and others when it develops on these members. And for that, first, as a rigid body, an equilibrium related analysis is required to understand the forces and moments acting onto this slender member. As compared to a slender member, I will say a full 3D body is all the dimensions are comparable to each other. So it's the bulky mass, you can say, which is the 3D body, you say, and the slender member is actually one of the dimensions much longer. You are slender when you are actually thin. So that's how you can understand non-technically also. Now, what's special about slender member? That slender members are plenty of examples, the buildings and bridges, or the ships, or the airplanes, or the machine parts. You can see where you are sitting here in the room. So on the floor, if you are on the upper floor, that will be supported on, you are on a slab, and the slab is supported by beams are supported on columns. They are all slender members. Aircrafts are not that rigid you think. Aircraft actually is a thin shell stiffened by beams and column type of members. Then ships are also like that. These are thin shell covered, under the cover there are beams, and they are called stiffeners, which are actually basically beams. So all are slender members in application. Now, to understand the behavior of the slender members, let us look into that. We are with the equilibrium requirement. We are still with the rigid body. Still, we do not consider two aspects. One is the deformation or the strain, and also the material properties related stress and behavior. That is kept pending for your next course. So next part of this course also, I think it will start from next topic itself. But still, so far, we have understood only rigid bodies and equilibrium. So with that concept in mind, now we are going to understand the behavior of slender members. So take an example of a beam type of structures. I say it is a beam type because this is not exactly beam. There is a slender member long enough, and it is subjected to an active load and an active moment, and it will be actually having supports. So there will be support reactions at the supports. And now I say that this beam is in equilibrium. If this whole beam is in equilibrium, then all the parts of the beam, if I separate out, they should also be in equilibrium to describe the static equilibrium as a whole. Now, what I do is that I just pass a hypothetical cross section perpendicular to the longitudinal axis of this beam to separate this beam into two parts. And I know that the whole beam was in equilibrium. Now the beam is divided into two parts. How can the individual parts be in equilibrium? There are active forces and moments as before. There are support reaction from one end as before. And for this part, to keep it in equilibrium, I can say in general, in 3D, I should have the components of the forces and moments acting onto the cross section. I will say this is a positive phase of the cross section because the positive axis, the x-axis, is emerged outward from this cross section, and also the y and z axis are parallel to this positive phase. So I can say that there are three components of forces and three components of moments. Three components of forces px. You will understand later why I have designated as Vy and Vz. So Px, Vy, and Vz are the three force components acting on this member cross section, and also Mx, My, and Mz are the three components of moments acting about the x, y, and z axis. I can say that if I correctly adjust the magnitudes, or I correctly understand the magnitudes of these, I can say this part of the beam with the external force acting on this part, with the reactive forces and moments acting on this part, and with the six components of force and moment resultants acting on this cross section, all this keep this part into equilibrium. Similarly, equal and opposite to these forces and moments should act onto the other part of the beam which was separated out. So equal and opposite of these forces and moments should work here. And I will say if this is a positive phase, this is a negative phase. And then from the negative phase, the x-axis as x dash will emerge outward, but that will be in the opposite direction of x. That is how, hence it is negative phase. So I can say that this part is in equilibrium with this combination of forces along with the external forces and reactions, and this part will similarly be in equilibrium with the external forces and reactive forces and moments with the equal and opposite forces of these internal forces. You can say these forces and moments, when I join these two parts of the beam, I get back my beams, and the internal forces being equal and opposite, the equal forces and moments, they will just vanish. They will equilibrate each other. So these were internal forces, and I have cut with a hypothetical section and exposed them. Hence, they have become external when I discuss the equilibrium of the part and not the beam as a whole. So when I discuss the equilibrium of the part of the beam, these parts will now become the external forces and moments. So the external forces and moments now will help in keeping this part in equilibrium. Now let us examine the significance of these forces and moments. So once again, you can just look at the same beam, but now I have drawn only this part. Only this part I have redrawn. So can you imagine that the Px force will pull the beam? Px force, if it is opposite direction, it will push the beam along the axis. Now Vy and Vz will try to displace laterally. So this is shear. So this is called the shear forces. This is called the axial forces. And can you just check? My is the moment about the y-axis. Suppose you hang this beam on the wall, this part of the beam on the wall, and can you imagine that My will try to bend the beam, still keeping it on the wall? It will bend like that. And now Mz, the Mz will also try to bend the beam, but now the beam will come out of the plane of the wall. So this is called the bending moment of the plane. So now you examine Mx. Yes, please.
What is the difference between shearing and bending?
You will understand. Please follow the lecture. Okay.
Okay, sir.
Now, shear is the lateral displacement, and bending is it just bend. And then you examine Mx, it does not bend because it is along the axis. Along the axis, it just twists. So if your imagination fails, just wait. Now see what is bending and what is twisting. So axial force will try to separate it out if it is tension. If it is compression, it will try to crush it here. If it is shear, it will displace it laterally. You have a scissor to cut a paper. Two pieces of the scissor component, it will put a tremendous shear force, and in between the paper, that small element will not be able to withstand that pressure, and the shear strain will be so high that the paper will be cut. This is called shear forces. The bending moment, it bends. If you stand on a small log of wood, you can experience that it will try to bend. It will not shear off. It will try to bend. If it is a thin wooden plank on which you are crossing a small ditch and there is a plank lying there. Suppose the bamboo bridges, when you cross, they will bend because it will not shear. And the torsional moment, if you go to the market and if you have that grinding machine where the wheats are grounded, so that type, there is a shaft. The shaft, while rotating, it will actually twist it. The rotational moment created by the motor will twist it. So this is axial force, this is shear, this is bending, this is twisting. Is it all right? Now?
Yes, sir.
So here are the effects and here are what we are doing, what we were doing. Carefully examine now. I have redrawn the same figure here for you, but you see, most popular application of beam is like the wooden plank, you stand on it upright. But this is a 2D problem. The beam usually vertically displaced either by shear or by bending. So what I say, we will take an example of a beam and start our journey for understanding of slender member behavior. And for that, a full 3D treatment may not be immediately required. And for the beam, I can switch off the AMX, which is a torsional effect. I can switch off the Vy also, which is the shear in this plane of the plane. But vertical shear, Vz, is definitely there in a beam. Mz is a moment which is not in this plane, but it will be in this plane. That also for time being I can neglect. So we can start our discussion with the effect on the slender member of this moment My and Vz. So this is called the bending moment in 2D plane figures and the shear force. So the bending moment and shear force. Do you understand it? Once again, this is general diagram. This is called the pull or push effect. This is called the downward shear, which will be most prominent in a beam. This is off the plane shear, which is also effective, but not that much popular application. The bending moment My is the most popular application of any beam where the load is vertically down. The Mz is also another kind of bending moment, but the bending moment occurs on horizontal plane, and the beam bends in horizontal plane. Usually the beam tries to bend on vertical plane. Yes.
If you take MZ, then it will be bending from width.
Yes, exactly. You take a small piece of what do you call, the packing material of your computer, any package material, make a small beam and try to bend it downward, upward, and sideways. You will understand the effect of My and Mz. Okay, so we have come up to this point that we are trying to understand that if we expose the beam by cutting through hypothetical sections, what are the moments and force components will be acting on the cross section, and then it will be actually we are understanding their effects and also agreeing that the 2D effects we can start with as a discussion of the beam. And if we agree this is a 2D, then there is no need for drawing the 3D diagram. We will have the projection of it. I will see from here towards the beam, and what I see is this. So My is now written as only M and Vz is written as only V, because I don't need the subscripts, because there is only M and V, nothing else. Similarly, this is for the left part of the beam. Now going back to our original beam diagram, you see the My and Vz is on this part of the beam. How about the corresponding forces on the other part? Yes, if you don't forget, you should put it M on the opposite side and V up. So this V is down, this V is up. This M is this side, this is anti-clockwise. Altogether, if you join the left part with the right part, you will get back your original beam. The hypothetical cross section in the middle, no forces moments acting in the. So that is why these are called internal forces. These are the title of this chapter is internal forces. So forces means in general, forces mean force and moment as well. effect. So you understand, this is the left part of the beam, this is the right part of the beam, and this is what we call, with respect to a right-handed system and with an agreement that we are discussing about the positive phase with positive axis X here, Y here, and Z here. With that, we have a positive sense of M and V, the bending moment and the shear forces. Now, we are after basically examining that if this is our diagram, I have put this hypothetical cross section at an arbitrary location. How about if I vary the location of the hypothetical cross section? I put it here, I put it here, I put it here, I put it here, I put it here. Will these quantities will vary? Yes, the quantities will in general vary. So that means there is a sense that I put the section at different locations along the length of the beam, and then I examine the variation of each one of them, and then I plot along the x-axis the variation of the quantities, and those are what are the axial force diagram, the shear force diagram, the bending moment diagram, and the twisting moment diagram. Is it clear to you? I hope so. So that's what we are going to do in this whole chapter. Through examples, we will learn now. But before we go, is there any doubt of any student right now?
So in the 2D part, why are you not taking Vx and Vy?
In the 2D part?
So yes, sir, this slide.
This is depending upon the application. Suppose in your building where you are sitting now on your chair, so that beam is primarily supporting a vertical load. If it is a vertical load, then the shear will be vertically down, and the moment will be mainly in this plane ZX. The moment will be acting on the plane ZX about the y-axis. This depends upon the application. So that is how we are discussing the most popular application. It does not mean the others are really insignificant. In some other application, this will be equally important or more important. Okay.
Okay, sir.
Come to the different kinds of beam. You are just wetting your feet with this chapter. So, you know, the beams can be two categories depending upon the support conditions. One is the statically determinate type of beams. One is statically indeterminate type of beams. Statically indeterminate type of beams is out of syllabus for you for this first year basic mechanics. We will just introduce at the last. So statically determinate means the problems are solvable using solely the equilibrium equations. Statically indeterminate means you cannot. So it means suppose simply supported beam means it has a pin support at one end and a roller support at another end. So now a continuous beam will be having an additional support, which definitely is better for sharing the load, but your equilibrium equation will not be sufficient to solve this problem. You need the information of deformation here to solve it. A cantilever beam has one end completely fixed and the other end free. A corresponding statically indeterminate beam will be a propped cantilever or end supported cantilever where you support a cantilever to share the load both sides. That is good for the beam, but that is bad for your now tackling the problem in basic engineering mechanics. So you have an additional support than required, and you cannot solve it through only equilibrium equations. A combination of simply supported and cantilever is possible with an overhang. This we'll call a simply supported beam with a cantilever overhang. And this is a combination of these two. Similarly, you can have a completely fixed support, and this is a statically indeterminate beam. Three equations you have, sigma fx0, sigma fy0, and sigma m0, and you have 6 unknowns. So and also the moment, so you cannot solve this problem. If it is 3D, you will have 6 unknowns, and if it is 2D, you will have 3 plus 3. So there are 3 unknowns. You have 6 unknowns, you have 3 equations. So 3 extra you need. Now, the beams can be categorized with respect to the loads applied. Beam can carry a concentrated force, beam can carry a uniformly distributed load. I can give you an example. Suppose you are having you are 70 kg mass. I should not say weight. You are 70 kg mass. This beam is suppose 2 meters. You are standing here. So that means 70 kg into 9.81, that much Newton is the force here directly at this point. Now, if you lie down and if you are 2 meter long, that 70 kg mass into 9.81 Newton weight will be uniformly distributed onto the beam. And the load intensity omega will be actually 70 into 9.81 divided by 2 Newton per meter. That's called uniformly distributed load. There can be a concentrated couple also applied onto a beam. And also, the beam may be having a triangular distribution. You might have seen this condition when suppose a lorry full of sand, it is just dumping the sands out and it opens the end hatch and the sand is sloping down. So at that time, it is triangularly loaded. So apart from that, there can be a general loading, and don't worry, you know integration, so you can integrate the whole area and you can get the total load. So this is called a triangular or non-uniformly distributed load. So I have extracted this nice diagram from Professor Merriam and Craig's book that how to get the total load. It's simply integration, but integration is basically finding the area under the curve, and you don't need to find out by integration. You just simply multiply the intensities to length, and here it is the area of the triangle, half base into altitude, and the CG is 2/3 of that. Here is the combination in a trapezium, but you don't try to find out the CG of a trapezium. You rather divide it into straight, uniformly distributed, and a triangular loading. And this is a general distribution where you can integrate and get the total effect, and also the CG you can find out from these equations. So
Excuse me, sir.
Yes.
Sir, why are we considering center of gravity here? We should consider center of mass, no?
It is center of it is a habit I am having from the actually civil engineering department. We deal with mainly gravity loads. That's the slip of the tongue is that. Yes, it is center of mass, you can say. In fact, if it is geometrically simple, the center of mass, center of gravity, and the centroid, which is purely geometric, nothing related to material properties, that will all these will coincide. And if this coincide, we will deal with actually centroid and not center of mass or gravity. You can call it centroid because you are dealing with geometry.
Excuse me, sir.
Yes.
Sir, then if the beam has uniform distribution, then why are we finding the center of gravity? Because it is in the middle, no? So the net force should act in the middle.
Yes, it is acting in the middle.
So then why are we finding X bar?
No, I don't follow. For the triangular distribution, it has to be 2/3 from this triangular tip end. Yes.
Sir, but you said that it should act on the center of mass only, no? So it should be at L/2.
You probably are confusing with the beam. I am talking about distributed loading. Okay. So this is the loading distribution.
Okay, sir.
The distribution of loading.
Okay, sir.
Not the beam. Okay. It is the loading on the beam. But so far, it is a geometric entity. You can get with a centroid. Okay, we'll come back to
Sir,
that. Yes.
Sir, one doubt, sir. In case of non-uniform distribution of load, we need to have the function omega, else we will not be able to solve the question.
Yes, if you don't have, and in engineering, you will not have. So it will be either discretized into small parts, or you will take it just segment by segment. Okay, in practical engineering. Practical engineering, you should not expect anything very smooth. Okay.
Okay, sir.
Come to the sign convention. Sir. Come to the sign convention. This is the most important slide out of all. Please, if you agree with this sign convention, you basically agree with this one. You basically have agreed with the axis orientation, right-handed system, and the positive moment and positive forces. If you agree with this, and if you see that you are dealing with My and Vz, and you are dealing with the part of the beam and looking towards your right, if you are looking towards your right, I can say that you see this moment My, now I am writing as M because it is a 2D problem, and the V downward is positive. We agree this is positive. We will say left up, right down. When I'm looking towards my right, right down is positive for shear. When I am on the right part of the beam looking towards my left, I expect the shear, positive shear, to be left up. I will come to this through examples. Be sure you will understand it very well. Don't worry. If you don't understand now, don't try to memorize. It will come
Can you say once again,
automatically.
sir?
Yes, please.
Can you say once again this sign convention?
This sign convention is automatically coming from this diagram. You have agreed that this is a right-handed system. So X, Y, Z, you do IJK vector, unit vectors in the same way. And you have agreed all the forces Px, Vy, and Vz are designated into the positive direction. The moments are also in positive direction. If you rotate from Y to Z, you get it out in this way, the moment vector. That is how the Mx is positive moment here. My, it goes from Z to X. And that is how it is a positive moment. If you have agreed this is a positive moment, and if you have agreed this is a positive shear, there should not be any problem in digesting this figure. That this, when you are onto the left part of the beam, you are looking towards your right, you expect the positive shear to be downward and the moment to be counterclockwise. Similarly, if you are with the right part of the beam, if you are with this right part of the beam, exactly equal and opposite forces will work, and onto the right part of the beam, you should have the sign convention opposite. Like this and this. Remember it if you can. If you don't, no problem. Through the example, it will come automatically. Now, two points. What is that if you say that I don't agree with you, I have my own sign convention? What is wrong with that? No problem. You have to solve it in your own sign convention and ultimately come out with an answer and tell me it is clockwise or anti-clockwise. I don't bother about your sign convention. But if you, all the textbooks, the popular textbooks we have prescribed to you, all follow this arbitrary sign convention. They need not follow. They can be different also. No problem. You can be different also. My advice is that don't try to invent now something which is already very simple, agreed, and everybody is following. Be with that. Who says that this is my right hand? If somebody says that I don't agree, this is your right hand, then I have no logic. But this is my right hand. I have been told from very beginning of life, I agree. So that's why there is no point in twisting unnecessarily. Okay. Now, the procedure, I think, any quick question? We are leaving this slide.
Sir,
Yes.
when we say left down, we see it from the right side and then we say left down for the shear.
Yes,
right?
I have not drawn a diagram for you because it will clutter your vision here. If you draw it, that your VZ will be on this figure, will be up. The MY will be here. So I have not drawn so that you just opposite to all these forces and moments, it will be opposite. And when you see from here, the 2D diagram, what you see from here is the 2D diagram I have drawn here now. This is a 2D diagram. This is your left part, the bigger part of the beam, and this is the smaller part of the beam. So now this was the MY I have drawn, and this MY I have not drawn. This is the V I have drawn, and this is the V I have not drawn. Okay, use the only sign convention you have to follow.
Sir, these parts are positive phase and negative phase.
Yes. If you agree, this is a positive phase. Positive phase means I am an observer, I am seeing as if the positive axis are emerging from that end. So now onwards, I will say this is a positive phase and this is a positive axis. So it's a negative phase with a negative axis. This X dash, anything on the positive phase, on the positive direction is positive. Anything on the negative phase, on the negative direction is also positive. Okay, we'll see it. We'll see it later. You take your pen, pull it from both sides. Pull it from both sides. What you are pulling with your right hand is the px, and what you are pulling your left hand is the force here. So you see, you are having a positive effect on the pen. The pen is in tension. Okay, the pain is in tension. How it is tension? Because on the right side you are on the right side you are pulling, and on with your left hand you are pulling it on the left side. Now tension is a positive effect, I assume. For me, tension is a positive effect, I assume. So I should have the negative phase in negative direction also positive. Okay. Chalo, we are losing time, no more. I think enough of fundamentals. Let me quickly go to the example. We should not waste much time for this. Only one example, if I explain properly, I believe that will be a very good thing for you. And rest of the thing, you can do it yourself. So,
Sir, can you please explain the last example which you have given for homework?
As a homework, I will not explain the homework. Okay.
Okay. Okay. Thank you, sir.
Chalo, let us do the simple thing in a very, very simpler way. This is the beam, simply supported beam with a central concentrated load. And somebody asked me to draw the shear force and bending moment diagram. Fine. This is just a minute. Hello? Yes, simply supported beam with a central concentrated load. I need to draw the shear force and bending moment diagram. First, settle with the equilibrium problem. Draw the free body diagram. So how you draw? You have a force here, reaction, you have a force here and a horizontal force because this is spin. But you understand, this is a vertical force applied. There is no horizontal component, so there will not be a horizontal force. Suppose you and me is carrying a beam and your friend is sitting on that. Then suppose he is 80 kg. Then we will be having 40 kg and 40 kg on both sides. And unless somebody pushes us from side, we are not having any horizontal disturbance. So that's it. So now how to approach? Simple, we have agreed, we'll take a section at a distance x. I will chant like a sloka like this. Take a section at a distance x. Remember this. Take a section at a distance x1. And I am going to examine two parts. So I may observe that maybe here there is no force unless I meet P. I am not sure if I cross P, the same equation will be valid. Maybe the equation will become different. So I may like to take another section here and then examine that how I can get the bending moment shear forces. Anyway, if you take the sections and then separate the bodies, first take at D. I have cut a section at D. Remember our first slide when I was cutting a beam? That same thing I'm doing. Now, if I cut the section, I will say that this is my shear force and bending moment, which is equilibrating this part. And already it is having a reaction. And for the right part, I have the equal and opposite moment and shear force equilibrating this part. So equilibrating this part and this part, I have a complete picture. Now, if I join, I get back my beam. Now, if I solve this equilibrium problem of the left part, I get with all vertical forces 0, P by 2 minus V1 is equal to 0. That means V1 is equal to plus P by 2 I got. V1 is equal to plus P by 2. That means I was right. I assume it, I got a positive value. That means, yes, indeed it is down. And now M1, I will say P by 2 into X1 is equal to M1. If I take moment about this, the moment of V1 will vanish and I will left out with M1 and P by 2 into X1. So M1 is equal to P by 2 into X1. I have not done this. I have left out for you. So now you vary X1 from here to here. So you get the bending moment, shear force and bending moment. So that's it. Nothing else. You similarly proceed for this section, you will get some answer. Or else, what you can do is that. But remember, once you cross the P, then the equation actually changes behavior. So it is better now the second, if you have cut a section here, these two parts, for you can select this part and this part for completing the diagram. You come from left, come from right. I'll show you the diagram how it is, along with these two free bodies. So consider this free body. What you are saying, there is a force P by 2 up. What you consider? Left up. If you see the left up, and if you see the right part, right down. So left part, right down is a positive shear. So once you take your fingers or palm and try to gradually expose from left part the beam. What you are seeing always a P by 2 force on your left, which is trying to displace laterally the beam. So that is how the shear force of the beam up to here is P by 2 positive. Now, if you cross this, the story is different. Now it is P by 2 and P force, as if the P force will push it down by P amount. Without considering this, come to this part. Now, if you consider your P by 2 force is on the right. So take your palm here and gradually expose and go up to here. You will see a P by 2 force which is actually up. But what you assume? It is left up, right down. Right down, you assumed is positive. Now you are seeing right up. So you are seeing right up. That may mean there is a negative shear force. So the shear force into this beam varies is from here to here with plus P by 2 and from here to here minus P by 2. This is happening due to the presence of P force, which is pushing this positive shear downward to negative. This is the work of this force to change the shear force. Later on, you will understand in your advanced year when you learn the deformations, it will be very clear to you. Right now, from equilibrium, I think it is fine. And for the moment, it is P by 2 into x1, and x1 varies from 0 to L by 2, so it is up to PL by 4. You come from here, you again see what you have considered. If you consider the left part, it will be anti-clockwise moment positive. If you are looking towards your right, it is anti-clockwise positive. Sorry. If you looking towards your left, it is clockwise moment positive like this. If you look towards your right, your anti-clockwise is positive. Now what you see from here, P by 2 is making it anti-clockwise. It is positive because you are looking towards your left. And once you are here, this P by 2 tries to rotate it like this. So this is also positive. So you have a positive bending moment diagram and a positive and negative combination of shear force. You will later on learn that this shear force is actually the slope of this curve. So it has a constant slope. That is why the shear force is also constant. The diagram is to be drawn. You need not join this line, which is not correct. Sometimes I draw this line to designate you that this is the shear force diagram, and also sometimes I shade it to make you visible to you. Never shade it in your examination. Never join these. So the shear force diagram along the length S with proper unit, it is this and this. And the bending moment with proper unit is this and this. So this is a positive bending moment, positive shear, negative shear. Is this absolutely clear to all?
Excuse me, sir.
Yes.
Sir, when we are approaching from the right side, basically we are imagining the origin to be at the extreme right. Is that how we are doing it?
Origin does not matter here. It is the element, what the force is trying to do. What I tell you, you draw this figure on the plane of paper. Then you put your palm to cover the whole figure. Then gradually expose this, moving your palm. Okay. Then what you see is this P by 2 force is trying to rotate it this way. So the moment you have considered, you can imagine when in a section you look towards your right, you have this my. Can you remember the first figure my? That was positive. That is why this P by 2 is positive. Now you consider that what this P by 2 tries to do, it tries to rotate it this way. Now you remember the second part of the beam in the first figure. In the second part, when you look towards your left, you have seen this opposite to my, the moment. So this was also taken as positive. Right now, it is a bit confusing. If it is confusing, to eliminate that confusion, you don't think like this. You leave it to the calculation for time being. You designate this correctly, and then automatically that V, if it comes positive, you are correct. If it comes negative, you are wrong. You revise it here.
So then there was a question in which a force and a movement both were applied. So how do we analyze the middle section? Like how do we write the equations?
Everything will come automatically from the reactions.
No,
So
sir,
this,
but the equations were not matching. Means if we take x2 from the left side in the problem with one force and one moment, it was not matching the conditions.
which one you are talking about? Are you talking about this question?
So it is after example 4 or 5. Thing.
Oh, you wait, please. Please wait. Okay.
Okay, sir.
Please wait. Let me explain.
So, so,
Yes. Any question related to
so
this
actually,
example?
yes, sir.
Yes.
So actually, if we consider the force at x1, so in downward direction, sir, then the SFD will firstly negative part and after L/2 distance it will be positive, sir.
Oh, this force is in the middle by chance. It can be anywhere. So what you say, this force should be where?
No, sir. I am telling that when we are drawing the diagram of shear force diagram, so when we consider at the point D, sir, the V force is in downward direction. If we consider it in upward direction, then sir, SFD diagram is coming to be negative in
This
0 to L/2
you mean to
part.
say this P force is upward?
No, sir.
No, sir.
Whole
Here
remaining
he
is
is saying V1.
V1.
V1. V1,
Yes, sir.
I agreed that V1 I will draw like this. I will never draw anything else. I will always draw when I am with this part of section. I will always draw it downward because that's what I have agreed in the very first diagram. I will never draw it upward. I will draw it like this. And when I draw for the right part, I will never draw it downward. I draw it upward. That's what I've agreed. Now, from the calculation, if I find V1 is coming to be positive, I will say I was right. If V1 comes negative, then I was wrong. That means I have a negative shear. Yes, you are correct. If your loading is opposite, if you still designate V1 downward, you must designate V1 downward. You will get a negative value of V1. That means you have a negative shear. That means the diagram will be like this.
Okay, sir.
How will
Okay.
calculate the value of M1?
M1, you take a moment about this point where V1 passes. If you take a moment, then V1 cannot create a moment there. Now,
The
P by
M1
T,
is also M1 also passes to that point now.
no, M1 is a moment. M1 is a moment. So, moment about that point, M1 will remain. It is not a force, it's a moment. So, moment is a free vector. Wherever it goes, it will remain. So, taking moment of all the forces and moments about this point, M1 will remain. If I take moment about this point also, M1 will still remain. It's a free vector. Okay, so taking moment about
M1
this
is
cancels V1, but not M1. But P2 has a distance, it remains. Okay.
Yes, sir.
Never for you are still confusing that the moment it will remain. Just be careful. Moment means somebody has given me with a force multiplied by distance. I am not bothered about how it is generated. Okay, I should have told you that this is a couple, not moment. But this is a bending moment designated as we have agreed. That is why I am calling it a moment. I should have told you this is a couple. No more teaching. It's self-evident. You have a uniformly distributed load. Do it yourself. What I have forgotten here is the V force, shear force here, and the M1, M force. So V downward, M like this. Solve the problem. I have written the equations correctly, but I have forgotten that. So shear force V X down. How will you write the equation? All upward positive, omega by 2 minus omega into x, and then it is downward or upward? It is downward. I am taking all upward positive minus Vx equal to 0. Omega L by 2 minus omega x minus Vx is equal to 0. That is the equation upward positive 0. And so you get Vx is equal to this. And if you put x equal to 0, you get a positive value. That means you are correct. You are right. The shear here is vertically downward. And that's how we designate it as positive shear here. It is right part. I am looking towards my right. So right down is positive and that's positive. Don't confuse. If there is any confusion, don't think. If there is any confusion, don't think. Designate it just what you agreed. And if it comes positive, you are right. If it comes negative, you are wrong. Go ahead.
Sir, can we say if one shear is positive, then another will be automatically negative?
Which one? This one?
Yes, sir. Can we say in general that if one
No,
shear
no,
is
no,
positive?
no way. No, you can only say that if something is downward, the other part I can say that is upward, but that does not mean anything. That does not mean anything because it is on the other part of the body. This is also positive here. You see, if you come to this section, the shear is anyway positive. Whether you consider the left part, whether you consider the right part, the shear is positive. Okay, you practice one or two problems, you will understand. That's not the logic. Here it is negative. Why? Here it is negative. You cut a section and then you cut a section here. Proceed similar way. You write down it. Suppose you are cutting a section and observing this part. So you automatically you will give a downward V. Solve the problem. You will find unless here you are getting a minus omega by 2 something. You will get it. You will get it. Then it will be convincing you that you are actually in opposite shear. That means your assumption of here it was correct, vertical shear here. But when you are here, you come up to here, cut it here, your vertical down assumption will become incorrect. But why do you bother? You go according to your convention. The result will tell you whether you are correct or not. It will correct you. Okay. Chalo. No more discussion. Look at it. You solve it yourself. The lessons learned. So a moment is applied like this. So counterbalancing forces will be in this direction. And the forces will be m by length. Moment by length is the two forces. You check m by L into L is m. Now you do again the same thing. Consider a section at a distance x. Draw the free body. Draw the equations. Write down the equations. And then you will find that m by L is coming shear force negative. Shear force negative. You practice and gradually it will become so well that you no need to cut a section and examine. You can say from the loading itself. And that is how we have fixed the conventions in such a way. Later on, you will be finding, you see, in your left part of the beam, it is down, you can say it is a negative shear. Right part up, that is also negative shear. Because you are left up, right down, positive. Later on, you practice this, that seeing that force diagram, you can draw the shear force diagram. But not now. Now you cut the section and do it. Gradually, you will realize that you no need to do so. Next problem, cantilever, do it yourself. Again, vertically down force, shear force is left up, right down. It is a right down shear, positive shear. But the moment will be negative because this will try to rotate this way. All the problems are arising why you know, because we are trying to understand the subject where the deformation is most important and we are not allowed to think in terms of deformation. When in the advanced year, you will think in terms of deformation, these things will become damn easy. Don't worry.
Excuse me.
So
sir.
next problem is a combination of, so lessons learned, if there is a concentrated force, the shear force changed abruptly. If there is a concentrated moment, the bending moment diagram changes abruptly. If there is a combination of force and moment, both the shear force changes abruptly for this force and the moment changes abruptly for this moment. You solve it yourself.
Excuse me, sir.
Answers. Yes.
Sir, in
Somebody
the
asked me
middle-
this question. Number 4, somebody asked question? Or you are asking this question?
Yes, sir. Fifth example.
Yes. What
Sir,
is the
if
problem
it-
here?
Sir, if we take the middle section and take the x1 from the left side,
Yes.
it is not satisfying the conditions.
Yes, it is satisfying. You just check it. You have, so do you agree with this free body diagram?
Yes, sir.
Now where you want to cut here?
Yes, sir.
You cut it and then what will you do? You assume a positive shear force downward and this. Then you sum up. So you put all forces equal to 0. So 3 point plus 3.75 minus 7 and then minus V1 is equal to 0.
Yes, sir. Sir, but here x2 are getting no. If we don't put it as x2 plus x.
You see here, if you cut it here, you will automatically get a minus 3.25. So it is here minus 2. You told here, I am here. It is minus here.
Sir, for moment for BMD.
Oh, BMD. BMD.
Yes,
Suppose you assume what in this section? You will assume this as the. So you will assume this one, isn't it? Like this. You will assume like this. Now we take a moment about this. What do you want to do? It will be 3 points. You take clockwise positive. So 3.75 into this distance x, then minus 7 into this distance. Then you have assumed this one minus m equal to 0. Probably you are doing it plus m.
Yes, sir, I am doing it plus m.
So why should you do it? Because repeatedly I am telling that this is the convention. When you cut it, your m, you have agreed it in this direction.
Yes, sir. Okay.
Chalo, ho gaya. This I will not explain. Do it yourself. It is nothing more than just combination of all the knowledge we have gained. There is nothing actually, nothing new. There is absolutely nothing new. You account for the loads one by one. Only thing, when you cut here, your distance is x1. So the area of the triangle will be half into x1 into this distance. This distance you have to find out from the ratio. From the ratio, you know this ratio by this ratio. So you find this by this equal. That pain you have to take. I'm telling you this is just painful, but it is not anything new. You do it yourself. I will send the photocopy of the one page of the book where it is solved. Fine. No more time. I have to wind up. So just 2 more things. One is that I don't want to discuss. You see it yourself. You are from JE, so you will be able to make it out that there is a treatment possible with integration, which will be extremely elegant. But don't expect your engineering system to be elegant. So this will not be of much use, but this treatment will open up your knowledge base. So this is the thing you will gradually find if you follow this treatment that dVdx is omega. That means rate of change of shear force is minus intensity of loading. And the rate of change of bending moment is the shear force. I have made a mistake. One student from the last class, he pointed out that Vdx will not actually, this should not be there. This should not be there. So this need not be there. I have made a mistake because I have taken a moment here. So that makes this Vdx b plus your at a distance dx vanish. So this should not be there. Anyway, you check it. So this is the moral of the story. And a problem which you have solved earlier has been solved using the formula of integration. It is so elegant, you will be prompted to learn this quickly, but you just keep it as a knowledge, but don't explore much. Okay. Now, next is that, just a minute, let me share the last slide. There is nothing new in the last slide. And I give it to you for your background study. Once you have understood all these things with me, I'm sure that, let me share it. Yeah, let me share it. So there are 2 more topics left, basically, but they are nothing new. One is the axial force diagram and another is the twisting moment diagram. So this is the axial force diagram and another is twisting moment diagram. There is nothing new. The tactics is same. Take a distance at an X, cut a section and examine this thing. Only thing difference is that for the axial force diagram, forget about the bending moment V and M. You are with the PX. That you have forgotten. PX in the beam PX, only PX. So this is what you are going to do and plot an axial force diagram. Again, the tricks is the same. At a distance X, take a section. This is the axial force diagram with positive, negative. You practice. And for twisting moment diagram also, it is the MX. Should not forget, there was an MX about the axis, longitudinal axis. Again, you draw the positive sense diagram and make sense that how the twisting moment diagram should look like. I think after the bending moment and shear force, these 2 diagrams are very, very easy. So that's it. I think the time is up. You have the next class. I have the next class also. So
Excuse me, sir. Can I
yes.
ask one last doubt?
So just a minute. Just a minute. So let me close the meeting, close the recording, and you are welcome. If you remain, I will answer one or two questions. So stop recording.